Hello students, today we will discuss Faraday's law and Lenz's law. These two are covered in electromagnetism, in electromagnetic induction. In the previous, we heard the terms electricity and magnetism. This electricity and magnetism, two terms are separated with each other, but Ampere's and Oersted prove that electricity and magnetism both are correlated with each other. How the magnetic field is produced? The magnetic field is produced by charged particles. Electric charge particle produces magnetic field. Suppose this magnetic field is, suppose I am taking a conductor or a wire. If field is passing to the wire, then obviously electric field is produced. So, the electric field as well as magnetic field both are related with each other. If there is a magnetic field, electromotive force is produced there. This electromotive force, we will treat this as some voltage is produced across the conductor. That voltage produced across the conductor is treated as electromotive force. This electromotive force is used for generating electric powers. Current carrying conductor produces the magnetic field. This magnetic field produces electromotive force. Using this electromotive force, it is used in electrical circuits as well as solar cells, solar panels, electrical power, so on. We will use this electromotive force. Next, we will see what is magnetic lines of force. Suppose I am taking a magnet, that magnet having north pole and south pole. So, the region near the magnetic field is treating as some imaginary lines I am concentrating. Those imaginary lines is called magnetic lines of force. Actually, it is not visible, but we will treat it as some imaginary lines. So, these lines, how it will pass? Always the lines is crossed from north pole to the south pole to the magnet. Just see in this figure, we have north pole and south pole. So, these magnetic lines of force is passing from north pole to south pole. How much field is there is depends upon the strength of the field. If the more field lines is there, then there is a more strength. If the field lines is very less, then the field is very less. As it is moving from north to south near to the magnet, the strength is more and more lines is passing. As we are going away from the magnet, the lines is lesser. One more observation here is the lines is crossing from north side to the south side. This is the image of magnetic lines. So, these magnetic lines are the imaginary lines, not visible lines. This we will imagine these lines. Afterwards, we will see this the same magnetic lines for the two magnets I am using. In the first magnet, I am using one north pole and south pole. In the second magnet, I am using two north poles. If one north and south, what happens? It will attract with each other. If north and south attract with each other, again the lines of force is there, magnetic lines of force. How these magnetic lines of force is passing? These magnetic lines of force is passing from north to south direction. In the figure A, the field strength is more. Near to the south and north pole, the lines are more, whereas we are going far, the lines is decreased. And again we have another one, figure B. In figure B, what we have? Two north poles. In the first figure, we have one north pole and south pole. North and south both are attracting with each other. Whereas if I am taking two north poles, what happens? It will obviously repel with each other. At the time these lines are not passing from north to south, just it is emerging outside, means coming outside from the magnet. That is the two magnets we are concentrating. One is north and south, another one is two north poles is straighted. Next, I am taking third image. What is the third image? I am taking one conductor. If I keep that conductor in the magnetic field, what happens? If the conductor is placed in the magnetic field, some current is produced. So, the field lines is concentrating in a horizontal direction and the current is taking in the vertical direction, which is proved by the right hand rule. In the right hand rule, the thumb figure represents current and the fingers, remaining fingers represents the magnetic field. So, total these magnets we are taking 3 to 4 types. What is the first one? One simple magnet of north and south, and second one I took the same magnet I am placing in the conductor. What happens? And another case is two magnets of same direction or other direction. If in two magnets, two north poles are in same direction, what happens? It will repel. If it is in opposite direction, it will attract. Another magnet I am choosing, that one is horse magnet or solenoidal magnet. So, total how many types of magnets we have? 4 types of magnets. First one is simple north south or two north poles or two south poles, that one I am choosing. Another type I am choosing one conductor. Third type of magnet I am choosing as a solenoidal. Here what is the meaning of solenoidal? Means the magnet in the shape of coil. If the magnet in the shape of coil, here also the magnetic lines of force are produced. The magnetic lines of the force near the coil is more, and these lines are passing from north side to the south side. As we are moving away, the field strength is less. So, this is third type of the magnet is solenoidal. We have another type of the magnet, that is called as horseshoe magnet. What is this horseshoe magnet? This is the magnet is in U shaped, and this horseshoe magnet is very famous and it is used in transformers, motors and electrical circuit, car, electrical vehicles. In all the axes, whatever the magnets we are using in present generation are horseshoe magnet. What is the advantage of using this horseshoe magnet? In horseshoe magnet, the north and south poles are kept near compared to the other magnets, whereas in solenoidal, one side we have north pole, another side we have south pole, but the distance is more between the north pole and south pole. The two magnets are close to two sides, north and south side are close to each other, and the field strength is good compared to the other magnets. So, we discussed 4 types of magnets. Now, before discussing our topic, we will see the few definition which is useful for the further discussions. What are those definitions we have? First definition is magnetic flux, next one is electromotive force, next one is inductive current. In that, what is magnetic flux? Magnetic flux means the strength of the magnetic field across the magnet. How much field is produced is called as the strength of the magnetic field. That strength of the magnetic field is called as flux. Another term we have electromotive force. What is this electromotive force? When magnetic field is there, means some voltage is produced. That whatever the voltage we are measuring, that voltage is called as electromotive force. If there is a voltage, obviously some current is also producing. Whatever the current is producing, we are calling that current as a induced current. So, we are using here 3 terms. First term is flux, next term is electromotive force, next one is induced current. Strength is represented by the flux, voltage is represented by electromotive force, and the corresponding current is represented as induced current. Next, we will see what is electromagnetic induction. Electromagnetic induction means when the magnetic field we are applying, some voltage is produced near the conductor. I am taking a current carrying conductor is placed in the magnetic field. What happens? Some field is, because of field, some voltage is produced. The voltage term here I am calling as EMF. Full form of EMF is electromotive force. So, the final conclusion of electromagnetic induction definition is, in the magnetic field some EMF is produced. That EMF is called as electromagnetic induction. Suppose I am taking some space, in that I am keeping a closed curve. In that closed curve, I am applying some magnetic field. If I apply some magnetic field, whatever the direction of magnetic field is, that is important here. The magnetic field is represented with B, and I am drawing a curve to that one. What is the curve here? N. I am here the loop in this figure. What is this figure represents? Take a space, in that keep a loop and apply magnetic field. Whatever the field direction we have, the normal component is also in the same direction. Here the normal component is represented with N and magnetic field is represented with B. Then what is flux? Flux is the product of field as well as normal component. Here the normal component is represented with N of x and field is represented with B. So, when this flux is positive and when this flux is negative, if the normal to the field as well as magnetic field means N and B both are in the same direction, at that time flux is maximum. If flux is maximum, the value of normal N equal to 0. Suppose we have another case when the flux is minimum. When the flux is minimum, the magnetic field as well as normal component N both are perpendicular with each other. If both are perpendicular to each other means both are in opposite direction. In this figure, how it is representing? Magnetic field is representing in outward direction, the arrows is outside. In this I am taking N also outside. If B and N both are outside, at that time flux is maximum. If B is in one direction and N is in another direction, at that time flux is minimum and it is represented with the negative sign. Next we will see, suppose I am taking a coil. To that coil I am connected to the galvanometer. One end of the galvanometer, one end of the coil is connected to the galvanometer one terminal, another end of the coil is connected to the second terminal of the galvanometer. Now I am placing one magnet consist of north pole and south pole. So here in this second figure what it represents is, suppose just I kept this magnet stationary, means not moving. If I am just near the coil, I kept the magnet without any movement. At that time there is no deflection in the magnet. Suppose that magnet is I am bringing close to the coil. At that time what happens? Some deflection will takes place in the galvanometer. So suddenly I am pushing outside the magnet. So here I am taking three cases. What is the first case? The first case is just the magnet is kept stationary. Stationary means not moving. It is in constant fixed state. At that time there is no deflection in the galvanometer. That is the first case. Second case is I am bringing that magnet near to the coil. If the magnet is brought near to the coil, there is some deflection is taking place in the galvanometer. Third case is what I am doing, that magnet is I am moving away from the coil. At that time the deflection is takes place in the opposite direction. That is represented in the figure number 2. What is the figure number 1? Figure number 1, again we have two images. Solenoidal, here coil of solenoidal is taken and a magnet is taken, the magnet having north pole and south pole. If we are keeping far away, if there is keeping far away, what happens to the lines of force? If I am keeping near, what happens to the lines of force? If I am keeping far, the lines of forces are not entering into the coil. If I am keeping near to the coil, the lines of forces are entering into the coil. This is the description of the image. Next we will see what is Faraday's law. This Faraday's law also proved that electric field and magnetic field both are close to each other in general. Now we will say how it is possible. Suppose magnetic flux is linked with some circuit. What it means? Some loop is there. In that loop, if flux is implemented, suppose flux is present means obviously electromotive force is also there. So in a region some magnetic field is there. If magnetic field is there means what it means? Flux is there. If flux is present, electromotive force is also present. So here we have two laws, Faraday's law 1 and Faraday's law 2. What is Faraday's law 1? Electromagnetic force EMF is related with the flux, that is the first point. Second point is electromotive force EMF and flux both are works in opposite direction. So in this magnetic flux linked with the closed loop, some EMF is produced. So what is the definition? The rate of change of flux is directly proportional to the electromotive force. Here electromotive force is taken as E and magnetic flux is taken as minus d phi by dt, where phi represents the flux. Why here minus sign? Minus sign represents the direction of the flux. Both are in opposite direction. That is the second law. So first law represents EMF is directly proportional to flux. That is first law. Then what is second law? In the second law we are discussing only about the direction. EMF direction and flux direction. Both are opposite to each other. Using this, what is the formula we are using? E equal to minus d phi by dt, where E is the induced EMF, phi is the magnetic flux, which the units of the magnetic flux is taking as a Weber. In this image, two laws is covered. What is the diagram represents? A solenoidal coil is taken, to that a bar magnet is brought near to the coil. So always remember the field lines are passing from which direction to which direction? North direction to south direction. To that one I connected galvanometer and it is showing deflection either one side or opposite side it is showing. So, flux is there, using flux EMF is produced, that is the first law. The first law, what is the formula of first law? E equal to minus d phi by dt. What is the second law? In second law we are concentrating only on the direction. EMF and flux both are opposite each other, both are in opposite direction. This is about the Faraday's law. Using this Faraday's law, now we will see the derivation part. In what is the basic first point of Faraday's law? We have formula E equal to minus d phi by dt. But we know flux. What is flux? Field into area. Here field I am choosing as a B and area I am choosing as a ds, some surface area. Here ds is the some surface area. So, in the first equation E equal to minus d phi by dt, I am substituting the value of phi. After substituting the value of phi, equation 2 in equation number 1, we will get field equation, electromotive force equation equal to minus d by dt times of, what is the phi value here? Integral of B dot ds. But we know what is E? E equal to integral of B dot dl. So, in the equation substitute E equal to integral of B dot dl. After substituting E equal to integral of B dot dl in the first equation, we will get the final conclusion as integral of B dot dl equal to minus d by dt times of B dot s. And here to this Faraday's law, I am applying Stokes theorem. What is the Stokes theorem? E dot dl equal to del cross E ds. In terms of electric field, if you are discussing, we can say that del cross E. Suppose I am discussing in terms of magnetic field, I will use del cross B. So, the previous del cross B is replacing with del cross E in the equation. So, in this equation integral of B dot dl place I am replacing with E dot dl. In place of B dot dl replaced with E dot dl. What is E dot dl? As per the Stokes theorem, del cross E times of ds. So, after simplification we will get del cross E dot ds equal to minus d by dt of B by ds. So, overall finally in terms of electric field what we are writing? Del cross E equal to minus dB by dt. So, this del cross E equal to minus dB by dt is the Faraday's law in integral form. So, what we discussed in this, what is Faraday's law, what is second Faraday's law, what is the case 1 and what is the case 2. In the derivation, this Faraday law formula equal to E equal to minus d phi by dt. The same Faraday's law I want to write in terms of integral. If the same formula if want to write in terms of integral formula, at that time we will write del cross E equal to minus dB by dt. This is about the Faraday's law. Next we will see Lenz law. What is this Lenz law and what is the difference between Faraday's law and Lenz law? Faraday's law discuss about the electro conservation of law and this one is discuss about the current. So, here in the Faraday's law we discuss that second law, direction is very important. Electric field, electromagnetic field and flux both are in opposite direction. So, what is the difference of formula for the Faraday's law and Lenz law? In Faraday's law we have formula phi equal to minus dB by dt, whereas Lenz law formula equal to phi equal to minus n terms of minus d phi by dt. Here n represents the number of turns. So, here finally what is the definition we will say? In the definition, the magnetic field is created, then the current whatever is producing is opposite to the flux that is produced. Here negative sign represents the direction of the EMF that is produced. As in this image we will see what is Lenz law is very clearly explained with this 3 images. What is the difference between the first image, second image and third image here? In the first image we are using bar magnet and I am using a loop, but the loop is far away from the magnet. Suppose magnet is here, the loop is far away. If far away, what happens? No current will flow, no signal strength is there. That is the case 1. Suppose case 2 is we have magnet and the loop I am bringing near to the magnet. If this loop is bringing near to the magnet, what happens? Some electric lines of force is produced from north pole to the south pole. At that time current is produced. In the second image, current is produced in the upward direction. whereas in the third image current is produced in the downward direction. So, what is the difference between the image 2 and image 3? In image 2 the loop is brought near to the magnet, whereas in image 3 the loop is going far away from the magnet. So, in the second image current is producing in upward direction using right hand rule, and in the third image current is producing in opposite direction. Opposite direction means here the current is producing in the downward direction. Why it is producing downward direction means the loop is brought outside or far away from the magnet. So, these three figures clearly shows how the Lenz law is working, and here another image is there, same type of image, but the difference here is I want to show the direction of EMF. In this, what is the difference between, again we have three images in this. What is the first image, what is the second image, and what is the third image? In the first image we have magnet and a loop. Magnet and loop, some distance is there, means both are far away. Here suppose I have loop, this side I have magnet, some distance is there between the first image, whereas in the second image suppose this magnet is brought near to the loop. What happens? Flux is increasing. Flux increasing is shown with more lines. In the first figure we have lines is less, whereas in second figure we have more lines. So, here the induced EMF is in the opposite direction. Flux direction is this way, EMF direction is in opposite, that is represented. So, flux forward direction, EMF is in opposite direction. This is the image. And what is this image? Suppose the bar magnet is moving far away from the loop. At that time EMF and signal strength both are in same direction. It is represented in the second figure and third figure. In the second figure, what is the direction? It is moving from north to the away, whereas EMF, see the direction of EMF is also moving away. So, these three figure represents Lenz law. In the first one, definition is flux as well as EMF, both are in opposite direction. The formula is phi equal to minus n times of d phi by dt. Next, what we have image? Next image is conductor is keeping near, conductor is keeping far away. If conductor is keeping near, we are getting current in upward direction. If conductor is keeping far away, we are getting current in downward direction. Next, what is the next image is showing? Induced EMF as well as flux, both are in same direction. When both are in same direction? When the magnet is placed near. Next, induced EMF and flux, both are in different direction when it is far away. This is the Lenz law. Next, we will see about the same one which is connected with the galvanometer. In the previous one, galvanometer is not connected. In the next image, galvanometer is connected. Same way magnet is moving forward as well as magnetic field is moved away. Here what we are observing from the previous one and this one, here galvanometer is connected. If you are bringing near, galvanometer is deflecting in one side. If I am taking away from the magnet coil, the galvanometer is deflecting in other side. Next, we will see the differences of Faraday's law and Lenz law. So, using Faraday's law, EMF is produced. Using Lenz law, we are discussing or we are concentrating on the current. Next, what is the formula of Faraday's law? E equal to minus d phi by dt. The formula of Lenz law is E equal to minus n times of d phi by dt. Here n represents the number of turns, and here in Faraday's law, electrical energy is converted to mechanical energy. Here conversion is not taking place, just we are concentrating on the current parameters. Next topic we will see expression of the induced EMF. In this image, what is the image? Which type of magnet is used? Is it horseshoe magnet or a solenoidal? Almost we are using horseshoe magnet. In between the horseshoe magnet, a conductor is placed. Across the conductor, the two ends of the conductor is connected to the galvanometer. Here I am concentrating on the two factors. What are the two factors I am concentrating? The first one is the direction of the current I am concentrating. Second one is the strength of the, first one is the direction, second one is the magnitude of the current. Both are current parameters only. The first one is the direction of the current, how it is. Second one is magnitude of the current, and the direction of the current is depends upon two parameters here. What are the two parameters? It is depending upon here to the rod is placed between the magnet, on how you are moving, on which direction the rod is moving, that is the one factor we are concentrating. Next, the magnitude of the current is depends upon the strength of the field. The magnitude is depends upon the strength. In the second image, what is the second image? Suppose I took a rod or a conductor. The conductor I am calling it as a PQ. I am placed in the magnetic field and I am moving here from left to right. The rod is moving from left to right, and here I am concentrating on velocity, length and x. Using this, the derivation flux we are calculating. What is flux? Phi of B equal to BLX. Using this, current value is calculated. What is the current we are getting? BBL by R, where R is the resistance, L is the length, V is the velocity and B is the magnetic field. Next one more thing we have, time varying magnetic field. In this time varying magnetic field means electric field is produced. Electric field is producing is how electric field is produced. Here the electric field produced is in the form of circle. See here we have one circle, in the middle we have charged particle. Whatever the electric field is produced due to the magnetic flux, and we have formula, whatever the electric field is produced is in terms of the circular rings, that is represented in the diagram. Whatever the electric field is there, that is in the form of circles. Using this one, formula is calculated. Electric field formula is E dot dl equal to minus d phi by dt. Here R is the radius. This derivation we got again from the Faraday's law. Next topic we have moving coil galvanometer. Actually, what is galvanometer? In our practicals, in our syllabus while doing practicals, we will observe this galvanometer in the laboratory. What is this galvanometer? Whenever magnetic field is there, some current is producing. That current is deflecting in the galvanometer. This is the galvanometer. To this galvanometer, two terminals there in the image. One black and another one is red. That black one we will do ground connection, red one we will give positive connection. This is the image of the galvanometer. Inside the galvanometer we have offshore magnet. I am placing a conducting wire. This conducting wire, copper wire, I connected to the coil. Whenever it is coiled and applied to the magnetic field, some torque is produced here. Whenever the torque is produced, at that time the galvanometer, in that it is the either moving to the one side or the tip point is moving to any one side. So, this is the, in this we have different components, inside components of the galvanometer. So, final here is some torque is produced. In the working principle mentioned, whenever torque is produced, current is conducting. So, this works on the principle of torque in the uniform magnetic field, and using that one the coil is deflecting in any one side direction. So, finally, the galvanometer deflection is directly proportional to the current it produced. So, here what I said, torque is producing. The torque I am taking as the B times of I times of NA. What is B here? Magnetic field, I is current, N is number of times and A is the area of cross section. Using this one, I calculated here current equal to C theta by N A B. Here N is number of times, torsional constant, here K is called as a torsional constant. Here also we are calculating current sensitivity. What is the current sensitivity? Suppose small deflection, but current is large, that is called as current sensitive. Large deflection means it is going to the higher value. For the small change in current, it is going to the higher value, then we will call it as a current sensitive. The formula of current sensitive is pi I by N. Another one we have damping correction. In this, what is actually damping correction means this galvanometer is deflecting, but while it is deflecting, some oscillations it is taking place. In these oscillations, the amplitude is increasing or decreasing. If the amplitude is increasing or decreasing, we will use two terms for terminology. The increasing amplitude is called as ballistic galvanometer, the decreasing is called as under damped galvanometer. Using this, the formula is calculated, and final formula for this galvanometer phi naught equal to phi 1 plus 1 plus lambda by 2. Again we have applications. So, we discussed about Faraday's law, Lenz law, electromotive force, flux, all these terms. Then where these are useful? These are useful in all electrical equipment whatever we are using. Inside we have flux, inside we have electromotive force, and current is producing, and without knowing us, in all the electrical applications we are using Faraday's law. So, in transformers, induction cookers, as well as in the converting energy from mechanical to electrical or electrical to mechanical, also in Newton's third law we are using this Faraday's law and Lenz law. Thank you.